These are the notes for LT5, the final learning target in our momentum and collisions unit. This is a very mathematical target, so perhaps you were in class but you just need extra help going over some practice problems. This would be the video to tune into. So target says, I can apply conservation of momentum to solve simple collision problems. This infers you are going to need a calculator. All right. Now, to start this thing out though, if you were in class, we watched the video of an astronaut, and probably in the International Space Station, he had 2 tennis balls. And what you saw is one tennis ball was at rest. It was hovering in the air because essentially there were no forces, or at least all the forces were balanced acting on it. And he took another tennis ball and he tossed it at this one. Let's just say he tossed it at 2 meters per second. It's almost like when you're playing pool, right? Playing a game of billiards, and the cue ball hits the 5. Maybe it hits the 5 ball, and the cue ball comes to a stop, and the 5 ball takes off. That's what we were able to see in that video. And I think if you just go to YouTube and type in conservation of momentum, and you see a picture of an astronaut, that's the one if you want to watch this. And so this ball that's coming at 2 meters per second will stop here, and then this one, it will make it like dash just to show where it's moving. That one takes off at 2 meters per second, and this guy stops. Okay, that's a perfect example of conservation of momentum, because remember, conserve, all that means is the momentum before the collision has to equal the momentum after. So the momentum of this ball and this ball before they collide is equal to the momentum of these 2 balls after they collide. Okay, they have to balance out. They have to be the same number. And that is just the law of momentum conservation. So conceptually, the concept isn't super difficult here. Okay, whatever you have before has to equal whatever you have after. Now, if we wanted to create a different momentum afterwards, let's say, we would have to exert an external impulse. Because remember, we don't always talk in terms of forces anymore. We're fancy. So we know an impulse is a force over a certain amount of time. So if we wanted to create an after momentum that does not equal this before momentum, maybe we would have a third ball out here, and it would come crashing in. All right. Now our momentum afterwards is very different. But if we just look at one system, those first 2, then the momentum before has to equal the momentum after. It's important to know that momentum can be transferred between objects. Okay, so when you looked at, you're playing the game of pool, the cue ball transfers this momentum to that 5 ball. Okay, so momentum can be transferred between objects. If you're in bumper cars at the Maple Syrup Festival and one bumper car hits the next one, that first bumper car might come to a stop, but it transfers this momentum to the next one. So overall, our momentum does not change. So conceptually, that's about it. It's the math that you've got to hang on for here. So this is you're gonna need a quiet spot and some focus. This sheet is on Moodle. There's extra problems on Moodle along with answer keys. Hopefully you can get to a printer, or you grabbed a copy of this in class, whatever the case might be. But at least follow along. Use a calculator. Don't get lulled to sleep by me here. Okay, use a calculator to solve some of this stuff. All right, so start out with, we can see there's 2 equations. Those equations are identical to the ones on your formula sheet. I just have them at the top of here. We have a 620 kilogram moose standing in the middle of railroad tracks, frozen by the lights of an oncoming 10,000 kilogram locomotive that's traveling at 10 meters per second. Engineer sees the moose, but he's unable to stop. This is going to be a happy ending, though. The moose just rides down the track sitting on the cow catcher. That's that triangle thing on the front of a train. And what is the new combined velocity of the moose and the locomotive? What you have to look at in these problems, it's almost a 3-step process. The first one is figure out, is it an elastic collision or an inelastic? If they are together at the end, it's inelastic. Okay, so this is where they would be together. If they are separate at the end, then you use the elastic equation. Okay, so that's our first decision. A combined velocity infers that this is inelastic. All right, so that's your first step. Your second step, you have to be willing to do some writing to solve these. Okay, these aren't mental math problems. You actually need to write some things out. So if we had a table, you decide one of these is going to be object 1 and the other is going to be object 2. It does not matter which you choose, but if I decide that the moose is object 1, I have to make sure I have all the moose's info in this column and I have all the locomotives info in this column. What info goes in those columns? It's based on the formula. Well, anything with a subscript 1, I list under object 1. Anything with a subscript 2, I list under object 2. Special situation, since they have a combined velocity, well, that doesn't have a 1 or a 2 because they share that. So I just usually split it right down the middle. And that's what we're looking for in this situation, the new combined velocity. So then we fill out the table. Object 1 is a 620 kilogram moose. That's its mass. It's standing in the middle of tracks. That means it is not moving initially. Mass 2 is the 10,000 kilogram locomotive. It is coming at the moose at 10 meters per second. Okay, so you just pick numbers out. So first step, which equation. Second step, then fill out the table. Your third step is to actually do the solving. And I'm not going to rewrite the equation here. If you need to, go ahead. But all I'm doing is substituting in. So mass 1 is the 620. The initial speed of the moose is 0. We add it to the 10,000 kilogram locomotive multiplied by how fast that locomotive, there we go, is coming at us. This is our before the collision. So before the moose hops on the cow catcher, that's this side, we know that this has to equal the after. Since they are together, we just combine their masses. We add 620 plus 10,000. We multiply it by the final speed, their combined final speed, because it says 2 in the equation. 620 multiplied by 0, that drops out. 10,000 multiplied by 10 is 100,000. We add these, so we're going to have 10,620 VF. It's no different than if you were in an algebra class and this is read as 10,620x. To solve for x, so to solve for this unknown, we divide each side by 10,620. Divide by 10,620. So up here, we go 100,000 divided by 10,620. In Moodle, it's going to say round to the 10th, and so it's going to be 9.4. So our final speed of the moose and the locomotive is 9.4 meters per second. So when you first look at this, you're like, wow, that's crazy. Like, there's a lot of stuff. Just be willing to go slow and take it step by step. Okay, problem 2. You're at your local maple syrup festival. You decide to play some games at a booth. I'm going to take some of the numbers out right now. You throw a ball forward in order to hit a bottle sitting on a shelf. Okay, so it's the classic game. You throw a ball, try to knock a bottle over. Assume you hit the bottle. It goes flying off. You're looking for the velocity of the ball after it hits the bottle. Now at these games, the ball does not stick to the bottle. They rebound, they recoil separate from each other. So you've got to decide, well, if they're separate, that's an elastic collision. Oops, poked a hole right through that. Okay, so it's an elastic collision. In terms of your steps, they're not really much different. You make a table. You pick something to be object 1, the other to be object 2. I'm going to say the ball first for object 1. The bottle is object 2. Again, it doesn't really matter what you choose. What does matter is that we line up all the 1s underneath the ball now and all the 2s underneath the bottle. So M1, M2. V1I, so the initial speed of the ball, the starting speed of the bottle. Final speed of the ball, final speed of the bottle. Then you go for the numbers. A 0.5 kilogram ball. You threw it with a velocity of 21 meters per second. Okay, I don't see this right now, so I'm going to skip it. So a 0.2 kilogram bottle. The bottle is at rest. You're not trying to hit a moving target. And the bottle flies off at 30 meters per second. What is the velocity of the ball? So this is what we are solving for in this situation. All right, V1F. So now we got to make sure we look at the correct equation. It's this one up here, and you just sub in the numbers. So m1 times its initial speed. So the ball's mass multiplied by how fast you threw it. We add that to object 2's initial before collision facts. So 0.2 is its mass. It's not moving. All of this before collision has to equal all of the after collision. So now we take the mass of the ball and we are looking for how fast it flew off. So there's our unknown. We add it to the mass of the bottle multiplied by how fast the bottle flew off after you hit it, which was 30. Now it's an algebra equation. We just solve. That drops out because we have a 0. So we go 0.5 times 21. We get 10.5 on the is all we have left on the left-hand side of the equals. 0.5 V1F. 0.2 multiplied by 30 is 6. Now, order of operations, that whole add, subtract, multiply, divide. If you divided before you subtracted this 6, you wouldn't end up with the correct answer. So order of operations says we subtract 6 from each side. So now we have 4.5 equals 0.5 V1F. Running out of space. Now we divide each side by 0.5. So 4.5 divided by 0.5, I'm just going to put this answer over here. 4.5 divided by 0.5 is 9. So 9 meters per second is the final speed of the ball after you throw it at the bottle. Right, so you may need to pause me, because we all know I go too fast sometimes, and go back and make sure that makes sense. Do you see where I substituted in those numbers? Now problem 3 and 4. These are just extra practice problems. And I just want you to look at some key words here. A new combined velocity. Okay, combined velocity infers that you and the polar bear, it's a sledding problem here, are together. So when you go off and work on this one, that's inelastic. Playing a game of pool against your friends, think about a cue ball hitting an 8 ball. Those balls don't have Velcro on them. They don't stick together. All right, so they're separate at the end. So you'll want to use an elastic equation for that. Now what I want to do is give you, well, I thought I had my answers written out here, give you the answers of both of these problems. I'll get you the answers of both of these problems. And so for number 3, I just realized I guess we're doing it together, because I threw away my sheet from yesterday. Hold on. Yep, we're going live with it. All right, so you're sledding down a hill at a speed of 15 meters per second. Out of nowhere, a polar bear is standing in front of you. Polar bear wants to sled too, hops onto the sled with you, continues down the hill. What is the new combined velocity of you and the bear as you finish your journey down the hill? Object 1, object 2. We already said it's inelastic. Okay, so object 1 I'm going to say is the bear. Object 2 I'm going to say is you, the sledder. Line up everything. There's an M1, there's an M2. There's a V1I, there's a V2I. You have the same final speed. So the bear is 500 and it is standing in front of you, so its initial speed is 0. You have a mass of 60 kilograms. You are heading towards the bear at 15 meters per second. We want to know how fast you two go off together. Inelastic equation. I'm going to put the bear stuff first. So here's the bear standing in front of me. Here I come at 15 meters per second. That has to equal, remember this is friendly, so the bear and myself are going to sled down the hill together, and we're looking for how fast. This drops out, so we're going to go 60 multiplied by 15. 60 multiplied by 15 is 900, equals 560. Just added those together, VF. And order of operations now, solving says that we divide. So we add first and then divide by 560. So we have 900 divided by 560 gives us 1.6. So the final speed of you and the polar bear is 1.6 meters per second. And I'm on a roll, so I might as well solve this one too. Playing a game of pool, you hit the cue ball. It gives you the speed it moves off your stick with. That cue ball hits the 8 ball, which starts at rest. Cue ball comes to a stop. With what speed does the 8 ball move off? They are separate, so it's elastic. You should be picking up on the fact the first thing we do is make the table. I'm going to call the cue ball object 1 and the 8 ball object 2. And then everything about the cue ball from the equation. Then everything about the 8 ball from the equation. Alright, mass of the cue ball is 0.17. I learned after teaching these problems, I did never realize prior in my life that the cue ball is slightly more massive than the rest of them on a pool table. Cue ball is tootling towards the 8 ball at 6 meters per second, and the cue ball comes to a stop, so its final speed is 0. The 8 ball starts at rest, and then we want to know how fast does it take off after you hit it. We substitute into the elastic collision equation now, so it's 0.17 times 6, so there's my cue ball info. I add it to my 8 ball info. Has to equal everything that happens afterwards. So the cue ball comes to a stop, and I add that to what happens to the 8 ball, and that, oops, V2F, that's ultimately what we're trying to figure out, is the final speed of the 8 ball. Both of these numbers drop out now because we have 2 zeros, 2 things were at rest. So 0.17 times 6 gives us 1.02 equals 0.16. We're looking for the speed of that 8 ball. Divide each side by 0.16. That's a 0.16. That looks awful. So 1.02 divided by 0.16. We have 6.375, which means 6.4 meters per second is the final speed of the 8 ball. Right? Okay, those are the notes and practice problems for LT5. There are more practice problems. I think I call them extra practice problems on Moodle. There's an answer key if you scroll. Good luck.